To a normie in the normal world, a product or device is considered premium if it's made entirely from metal. Doesn't matter what type, pot, steel, brass, aluminum, whatever tickles your fancy. In a different world, one where there's always cutting oil on your hands and metal chips in your shoes. In a world where aluminum is a wet noodle and plastic is for children's toys. The world of the machinist. For a machinist, unless it's made from steel, it basically goes in the trash, just like this Er32 Collet, which I don't actually have because, well, I forget things sometimes. It happens. So, B-roll. Er32 Collets are typically made from tool steel and come in at a whopping $10. Now, if you're not a weird metal breather like me, a collet is essentially a spring or a clamp. The slits in the body allow it to be compressed as it goes into a taper, clamping down on, well, whatever you shove into its mouth hole. This could be some stock, a cutting tool, your fingers, dealer's choice. As always, there is a problem. Otherwise, I wouldn't be shouting at the camera right now. Collets only work for a very specific size and range. In this case, anything measuring from 0.46 to 0.5 inches round stock. So really not a big range, which leads people to typically buy entire sets of collets. So that $10 purchase, well, it just ballooned up to $150 and all of your monies have turned to tears. Lack of funds isn't my only problem though, slippage. Tapping is one of those operations I'll do just about anything to avoid. I'm not sure there's any greater pain in this world than breaking a tap in your brand new machined part that you've spent hours working on. Along with that, tapping by hand is a boring and tiring slog. The simple solution would be, well, just let a machine do it for you. Power tap, throw it in a drill chuck and send her on its way. And that works great, right up until everything just starts slipping. And it just won't stop no matter how hard you reef on it. It just keeps slipping. Well, there is a simple and commonly available solution to your problem. Tapping collets. Well, you could probably just not use dull taps, but that's just crazy talk. Tapping collets, like their round shank brethren, work by clamping around the tool, but they have a special feature, a square drive in the back. This essentially makes it impossible for the tap to slip, although I'm sure someone out there has tried. This geometry is also what makes tapping collets exceedingly expensive, and what leads me to time and time again fall victim to slippage. That is, until I had an idea. Couldn't I just 3D print my own tapping collets? I mean, sure, resin costs money and everything, but in my sick and twisted mind, if I make something, it's basically free. Plus, I'm not the only one to have this idea. People have 3D printed Er32 collets before. But from what I can tell, they all seem to be the traditional round shank variety type, which honestly sounds like a terrible, terrible idea. Like I said in the beginning, aluminum is soft, so plastic, there's just no way. There's no way it's gonna shake, rattle, and roll all over the place. But a tapping collet, that could be a good idea. You see, I don't have to worry about concentricity or run out or clamping pressure. And in fact, the flex from the plastic could almost be a bonus in that it might keep my taps from snapping when I, forget to change that quill stop. So I just dove right in. Came up with a quick concept and threw it over to the 3D printer. Typically for this kind of rapid prototyping, I would use FDM printing. It's really fast to iterate and you don't have to deal with all the sticky, stinky chemicals and alcohol and all that jazz. But in this case, we need these to be as strong as possible, which means printing 100% infill. And I just happen to have a high strength resin already loaded into my printer. So sometimes the stars align. Sidebar, 3D printing is hands down the greatest thing ever. Like, no joke, from initial idea to physical prototype took me like less than 3 hours. And half that time I just spent watching YouTube while the machine did all the work for me. This speed actually came in really handy because before the print ever even finished, I was like, that's not gonna work. I mean, it did sort of work. It managed to tap 3 holes, but it sort of turned into multiple pieces afterwards. Not a major hurdle though, because the problem was actually pretty obvious. There are way too many clamping slits in the body. The original design had this many because, well, it's made out of steel and it needs to actually be able to compress. In plastic, it just turned it into an absolute banana. Plus, all those slits weakened the corners of the square drive considerably, and that's ultimately what decided to say bye-bye. So, I kept everything the same and just eliminated a handful of them and how far down the body they go. Sent it off to the printer and it worked great. At least, I think it would have, because I actually never finished those because, once again, I had another idea. Why am I following the original design? I'm not machining these. I'm 3D printing them, which opens up a whole new world of possibilities when it comes to design. So, to get a little fancy, I decided to change the slits to curves, you know? It looks cooler, certainly, but it should also actually be stronger, at least in the corners of the square drive. And it will be at least stronger in one direction, and the other one technically weaker, but as long as I never turn left, I'll be golden. The whole gang's here, and I gotta say, they are looking sharp. The real question though is, will they actually work and live to tell about it? Well, I happen to have a bunch of parts laying around that are in desperate need of some tapped holes. In this case, mild steel, 8 parts, 1/2 inch diameter, all need a 3/8-16 tap driven. So, here goes nothing. Shockingly, it just worked. Hole after hole, it shoved this tap through without incident. It did make a few creaking noises here and there, and I could definitely feel it compressing more than usual with the collet wrench. But still, collet came out unscathed and without a mark on it, which is particularly impressive because I managed to throw my mill into forward instead of reverse, causing the whole thing to crash. Luckily, the belt slipping failed before the tap or the collet. 3/8-16 is good, but let's put it to a real test. How about a 1/2 inch-13? Mild steel again, 1 inch thick, just 1 part though. And if it's able to do this, I'm pretty sure it'll be able to handle anything I can think of to throw at it. Well, not surprised this time. It worked. It worked again. No problem. And just like the 3/8-16, it came out looking brand spanking new. Will these hold up over time is certainly to be seen, but honestly, I would be shocked if they don't. And what's even better is you can actually totally 3D print these yourself. The files are available below, and the original model is parametric, so you can adjust it to fit whatever tap you need. From start to finish, total win. Super happy with this project. Saved myself, hopefully, some money, maybe, I don't know. But one thing, it's got me daydreaming about all sorts of other machinist accoutrement I might be able to 3D print. But that's all I got. Later.